Lesson 3.3, Stopping Side Distance and Decision Side Distance. After completing this lesson, the student will be able to appreciate the need for providing stopping side distance and decision side distance. Also will be able to identify influencing factors and understand the basis for suggesting design values. What is side distance? The length of the road visible to a driver is the available side distance. It is the actual length of the road, not the straight line distance. It is basically the actual length of the road visible to a driver. There are possibilities that available side distance, there could be some sorts of obstructions. Obviously, for a straight road on level ground, there is no problem in terms of the side distance. However, it is impossible or impractical to think of a road which will be absolutely straight and on level ground. There will be horizontal curves, vertical curves and also intersections, which are integral part of road system. So, these are the potential places where there could be restriction in terms of available side distance. Intersection, there could be some establishment, some buildings near the corner which may obstruct the line of sight. Similarly, the vertical curves where there is convexity upwards, which is called as summit vertical curve, due to the road itself there could be obstruction to side distance. Wherever there is horizontal curve, again due to some development, some buildings, shops in the inner side of the curve, the line of sight may be obstructed. So, there are three potential places: intersection, horizontal curves and vertical curves, where there could be possible obstruction in side distance. Next, our topic today, one of the topic is stopping side distance. Stopping side distance is the length of the road required for safe stopping of a moving vehicle. For various reasons, drivers they are required to stop their vehicles. So, at least sufficient length of the road should be visible to a driver, so that the vehicle can be stopped under emergency condition. We will see later in the subsequent lesson that there are other types of side distance, but the minimum required side distance is SSD or the stopping side distance, because stopping is the elementary or the most essential maneuver that is required. Vehicles must be able to stop. So, this is required for safety. So, this is the minimum required criteria, that the available side distance should be at least equal to the stopping side distance. So, stopping side distance is also called the absolute minimum side distance, because that is the absolute minimum requirement. Criteria for measurement. Now, when we are talking about the side distance, it depends on what is the height, that means the level for driver's eye, and what is the height of the object that we are talking about. You can appreciate the available length of the road or the length of the road visible to a driver will depend on the height of the seat, particularly the eye level, height of driver's eye above road surface, and also the height of the object. If we consider more height of the object, obviously available distance, side distance will be more. Similarly, if we consider higher height of eye level above road surface, again the available side distance will be more. You can see, one can understand easily that the length of the road visible in front of a car is generally lesser as compared to the length of the road visible in front of a truck. So, it is necessary to specify the height of driver's eye above road surface and also the height of the object when we are talking about the stopping side distance. So, here as per Indian Roads Congress, the height of the driver's eye above road surface is taken as 1.2 meter and the object height is taken as 0.15 meter. As per AASHTO, American Association of State Highway and Transport Official, as per AASHTO requirement, height of driver's eye above road surface is considered as 1.08 meter and the height of object above road surface is taken as 0.6 meter. These are design values. Now, the height of the object as taken by AASHTO is much higher, 0.6 meter, as compared to the object height considered in Indian condition as per Indian Roads Congress recommendations, that is 0.15. Now, the value of object height is based on certain consideration. Number 1, rationalization of the size of object that may be encountered. What are the types of objects that drivers normally encounter while driving the vehicles? Number 2, impact on construction cost. As I indicated earlier, if we consider lesser object height, the requirement or the requirement of side distance will be more. So, obviously, to provide better standard, maybe a flatter curve will be required. So, the construction cost will go up. So, there is a possibility that a value lesser than 0.6 meter may increase construction cost substantially. 0.6 meter height is actually the height of passenger car tail lights. That is the basis for taking 0.6 meter as recommended by AASHTO. Third, driver's ability to perceive and react. It is found that at high speeds, most drivers are limited in their ability to detect small objects. So, when the object height is decided, which is recommended as 0.6 meter as per AASHTO, all these points are considered. Let us try to see what are the factors affecting stopping sight distance. Number 1, perception reaction time of driver. 2, speed of vehicle. 3, efficiency of brakes. 4, frictional resistance between road and tires or deceleration rate. As per IRC, the frictional resistance or the coefficient of friction is considered while calculating the stopping sight distance, while AASHTO calculates or AASHTO recommends values which are based on the deceleration rate. And fifth, longitudinal gradient of road. All these 5 factors, they actually influence the stopping sight distance. How? Let us discuss. First, the perception reaction time. Whenever there is a necessity to stop the vehicle, how it happens? First of all, may be an objective visible to driver, it goes inside the mind, that information, it is analyzed or processed, and the driver makes decision that yes, he needs to stop the vehicle. So, accordingly he put pressure on brake pedal, and that is where at that point only the effective application of brakes that starts. So, there is a time gap by the time the object is visible to a driver and by the time the brakes are applied effectively. This time is considered as perception time. Sometimes this time is split into perception time as well as the brake reaction time. Perception time is the time lag between the object, once the object is visible and by the time the decision is made that yes, brake should be applied, and brake reaction time is the actual time which is then required for effective application of brake. But often these are considered together. So, we are calling this time as perception reaction time, which includes perception as well as the reaction. So, this is the time taken from the instant an object is visible to the instant brakes are applied effectively. From your logical mind, you can understand that this time depends on several factors. For example, characteristics of driver, what is his age, what is the mental alertness. Similarly, the characteristics of obstacle, whether it is moving object or whether it is a stationary object. Third, speed of vehicle, driver's alertness also depend on speed of the vehicle. Other is also the in general the required distance for stopping will be more as the speed is more. It also depends on the distance between vehicle and object and also characteristics of vehicle. Not that every vehicle type, a car, a bus or a heavy commercial vehicle, it depends on the type of vehicle, the type of mechanism or mechanical system which is there in the vehicle. So, it depends on the characteristics of vehicle also. So, perception reaction time is not really a fixed value. It varies on drivers, vehicle type, type of object and so many other factors. But for design we need a single value, because the road system is to be designed for a single value. So, what should be the basis or what should be the major considerations when a single design value is selected? Let us have a look. Basis for design value. Design value should satisfy requirements of nearly all drivers under most operating conditions. So, nearly all drivers may not be 100% and under most operating condition, not under all operating conditions. If we try to select a value which will satisfy the requirement of all drivers and under all operating condition, the value will be substantially large. Obviously, there will be an impact on the construction cost and the overall economy. So, design value is selected in such a way that it satisfies requirements of nearly all drivers under most operating condition. It is also worthwhile to mention that required time is generally higher under normal conditions than under alerted conditions. When drivers are alerted, yes, there could be a possible object or maybe there is a school ahead, they know it. Then under alerted condition, the reaction time is lesser. It is also found that a 2.5 second reaction time, a time of 2.5 seconds exceeds the 90th percentile of reaction time of all drivers. One can justify, that means if 2.5 seconds value is taken, then that will exceed that exceeds the 90th percentile of reaction time for all drivers. So, 2.5 second reaction time is generally acceptable and accepted for design purpose. However, for extremely complex operating condition, 2.5 seconds time reaction time may not be adequate. We shall come back to this discussion and that will lead us to the decision side distance. We shall come back to that part later. Now, it also depends on the speed of the vehicle. Obviously, higher the speed, higher will be the required SST, because it will take more or longer time for the vehicle to stop once the speed is higher. Third, it depends on the efficiency of brakes. What we understand by 100% brake efficiency? 100% brake efficiency means the wheels are fully locked, so there is no rotation. This is not desired from safety point of view, because there will be skidding, and once the vehicle skids, driver will not have the required or desired control on the movement of vehicles. So, therefore, it is not desired to have 100% braking efficiency while applying brakes. It depends on the frictional resistance between road and tires. The coefficient of friction depends on speed of vehicle. Higher the speed, lesser will be the value for coefficient of friction. Type and condition of pavement, both. Type means whether it is bituminous pavement or water bound macadam or an earthen road or a concrete road. What is the type of pavement or the type of surface? So, obviously, coefficient of friction will depend on that, and it will also depend on the condition of pavement, whether it is dry or wet. The coefficient of friction value is normally much lesser on wet pavement as compared to the pavement which is in dry condition. Type and condition of tire, that also affects the coefficient of friction. Old tires, worn out tires which are practically flat, and new tire with very good treads, they behave in different way. And also the brake efficiency, as I told, if it is 100% brake efficiency, wheels are completely locked against rotation. So, obviously, higher coefficient of friction will be applicable within the braking distance. Yes, coefficient of friction varies depending on all these factors, but for design purpose, Indian Roads Congress have recommended a value in the range of 0.35 to 4 depending on the speed of vehicle. For higher speed, the values are lesser. How the stopping side distance is calculated? As I mentioned earlier, it is the distance vehicle travels during the thinking time. In a more refined form, it is now the time during the reaction or the perception reaction time. We have understood what is perception reaction time. So, the vehicle travels in its original speed during the perception reaction time, what is known as lag distance, and then once brakes are applied effectively, vehicle will again travel some distance before it stops. So, that distance is known as braking distance. So, stopping side distance is equal to lag distance plus braking distance. Lag distance we can calculate easily. It is the reaction time multiplied by the speed. So, if v is the speed in meter per second, then it is simply v multiplied by t, where design value of t is 2.5 seconds, or if v is expressed in kilometer per hour, then it is 0.278 v into t. T is in second and v is in kilometer per hour. Now, the braking distance is actually the distance covered by a vehicle to come to stop after application of brakes. Now, how this distance can be calculated? The basic equilibrium or the basic equation is work done in stopping equal to the kinetic energy. This is the basic equation used by Indian Roads Congress and also by AASHTO. However, AASHTO, rather IRC, Indian Roads Congress, they use coefficient of friction for calculation of stopping side distance. So, here the diagram is shown where a vehicle weight is W, show the frictional force what is generated is F equal to is indicated as F, which is equal to coefficient of friction multiplied by the weight of vehicle. So, capital F is equal to small f multiplied by W. So, work done is frictional force multiplied by braking distance. So, if the braking distance is L, then the work done is force multiplied by braking distance. So, coefficient of friction multiplied by weight multiplied by length. The kinetic energy equal to half into mass into velocity square. So, half mv square, m is the mass, equal to half w by g into v square. So, if we equate these two, work done equal to kinetic energy L is v square by 2 g f, where L is the braking distance in meter, v is the speed of vehicle in meter per second, f is the coefficient of friction longitudinal. We are talking about the coefficient of friction, which is longitudinal coefficient of friction, and g is the acceleration due to gravity 9.8 meter per second square. Now, if the speed of vehicle is expressed in kilometer per hour, then with multiplier it will become v square by 254 f. In this case, v is in kilometer per hour. So, therefore, the stopping side distance is lag distance plus braking distance. So, either it is v into t plus v square by 2 g f if v is in meter per second, or it is 0.278 v t plus v square by 254 f. In this case, v is in kilometer per hour, and in both cases t is the perception reaction time in second, which is the design value is 2.5. Coming to the AASHTO recommendations, it is found that approximately 90% drivers, they decelerate at rates greater than 3.4 meter per second square. Also, it is found that such decelerations are within driver's capability to maintain steering control during braking on wet surfaces, because wet surface is critical as compared to a dry surface. So, even on wet surface, drivers can very well keep control on the movement of vehicle with deceleration 3.4 meter per second square. At the same time, most vehicle braking systems and tire pavement friction levels are capable of providing a deceleration rate of at least 3.4 meter per second square. Considering these three aspects, AASHTO recommends a fixed value of 3.4 meter per second square, fixed value for deceleration of 3.4 meter per second square for the calculation of stopping side distance. It does not calculate SSD based on coefficient of friction. instead of using coefficient of friction, a constant deceleration rate of 3.4 meter per second square is used. Suggested deceleration rate corresponds to a value of coefficient of friction of about 0.35. So, whatever braking distance value will be obtained by considering a deceleration rate of 3.4 meter per second square, nearly same value will be obtained if the coefficient of friction is assumed as about 0.35. Using deceleration rate, the braking distance can be expressed as 0.039 v square by a, where a is the deceleration rate and v is in kilometer per hour. It is basically the earlier equation v square by 254 f. If we replace f by a by 9.8, 9.8 is the value of g, then this equation we will get, that is braking distance equal to 0.039 v square by a. V is in kilometer per hour and a is in meter per second square. What is the effect of grade on stopping side distance? No doubt the stopping side distance on grades will be different from what we got on level road. We can also estimate or calculate the effect of grade on stopping side distance. Look at this sketch where W is the weight of the vehicle and alpha is the slope. Here if we consider an upward slope, then this weight we can split it into two components, two parts, W cos alpha in the perpendicular direction and W sin alpha in the parallel direction. So, therefore, the frictional force is coefficient of friction multiplied by this component of weight in the parallel direction, that is W sin alpha. So, force equal to coefficient of friction into weight into cos alpha. So, work done is total is W sin alpha plus this frictional force, which is F capital W weight of vehicle cos alpha multiplied by the length. So, here if or normally that slope is small. So, for small alpha, cos alpha is approximately equal to unity and sin alpha is approximately equal to tan alpha, which is nothing but taken as n here. N is the percentage of grade divided by 100. So, if we say 3% grade, it actually means 3 by 100, that is the value of n. So, kinetic energy is, as we calculated earlier, half mv square. So, if we make work done equal to kinetic energy, then we get length is v square by 2 g into f plus n. In this case, L is the braking distance in meter, v is the speed of vehicle in meter per second, f is the coefficient of friction longitudinal, g is the acceleration due to gravity 9.8 meter per second square, and n is the percentage of grade divided by 100. So, if there is an upward slope from the equation, you can understand that the required stopping side distance will be lesser as compared to the SST on plain or the level road. Similarly, if there is a downward slope, then n will be minus n, the sign will change. So, you can understand that the required stopping side distance value will be more when it is a downward grade. So, for upward grade, the required SST will be lesser as compared to the required SST on plane, and downward grade it will be reverse. That means, downward grade the required SST will be more. Now, if again V is expressed in kilometer per hour, then it will be L will be V square by 254 into F plus N. So, therefore, whenever there is a grade, the required stopping side distance equal to lag distance plus braking distance. So, it is V t plus V square by 2 g into F plus N. Here V is in meter per second, T is in second, or 0.278 V t plus V square by 254 F plus N. Here if V is expressed in kilometer per hour. Now, ASTO, the basis is again same, basic understanding is same. The only difference is ASTO does not calculate it on the basis of coefficient of friction, it rather uses the deceleration rate. So, look at this sketch here. F is taken as mass into acceleration. The component parallel component is taken as W by G into A. As per when we try to derive it based on IRC, we used small f into W cos alpha. Here we are using F equal to mass, force equal to mass into acceleration. So, W by G into A. Remaining is the same. So, work done is W sin alpha plus W by G into A. This is the force multiplied by L, the length, and kinetic energy is as usual W by G V square, half of W by G V square. So, if we equate these two, we can find out L as L equal to V square by 2 G into A by G plus N as shown here. Here L is the braking distance, V is the speed of vehicle in meter per second, A is the acceleration rate in meter per second, G is the acceleration due to gravity 9.8 meter per second square, and N is the percentage of grade divided by 100. Now, again if the speed is expressed in kilometer per hour, then the equation will be L equal to V square by 254 into A by 9.8, which is the value of G plus N. So, the stopping side distance is V into T plus V square by 2 G into A by 9.8 plus N if V is expressed in meter per second, or it will be 0.278 V into T plus V square by 254 into A by 9.8 plus N as shown here. Here V is in kilometer per hour. Now, variation for trucks. The recommended design values for SSTs, particularly the H2 recommendations, are based on the considering or based on the car traffic movement. It do not explicitly consider design of or design for truck operations. Now, trucks, especially the larger and heavier units, need longer stopping side distance due to the vehicle characteristics. However, there is a balancing factor, that is height of driver's eye above road level. In case of a truck, it is much higher as compared to the height of driver's eye for cars. So, that is a balancing factor. So, because of the higher height, drivers can see longer distance of road. So, the available side distance are generally higher for trucks. Therefore, separate stopping side distance values are not recommended for design purpose. However, one must remember that there is a special situation where this more height of truck drivers will not be meaningful or useful. That is, when horizontal side restrictions occur at the end of long downgrades. At that conditions, the speed of trucks will be almost equal to speed of cars. It may be even more if the grade is long enough. So, speed wise it is comparable, but driver's eye, their level, its level or height of driver's eye above road surface, that is not at all advantageous under this special condition. So, wherever horizontal side restrictions occur at the end of long downgrades, one must try to provide more side distance than what is recommended as SST under normal conditions. Let us take an example. Let us consider two vehicles which are approaching each other. One is travelling at 90 km per hour speed, the other is travelling at 50 km per hour speed, and it is a single lane road. That means, it is a narrow road. The coefficient of friction is 0.75, but brake efficiency is only 50%. Now, what will be the minimum side distance required to avoid a head on collision? Obviously, we have to calculate the SST. Now, effective coefficient of friction is only 0.5 of 0.76, because the brake efficiency is 50%. So, that is 0.38, that will be the design value for the coefficient of friction. Now, we can calculate the lag distance for the vehicle travelling with 90 km speed. It is 0.278 into 90 into 2.5 second reaction time. So, that is 62.55 meter. For the second vehicle, which is travelling at 50 kilometer per hour speed, the lag distance is again 0.278 into 50 into 2.5, that is 34.75 meter. Now, we shall calculate the braking distance v square by 254 f. So, for the first vehicle it is 90 square divided by 254 into design f is 0.38. So, that is 83.92 meter. For the second vehicle it is 50 square, because 50 is the speed, divided by 254 into f, the value of design value of f is 0.38. So, 25.90. So, required stopping side distance for the first vehicle is lag distance for the first vehicle plus braking distance for the first vehicle. Total is 146.47 meter. For the second vehicle, required SSD can be calculated in the similar manner, lag distance plus braking distance, and total is 60.65. Now, since it is a single lane road, which is a narrow road, that means to avoid head on collision, the vehicles should be able to see each other, and the distance in between should be equal to SST required for the first vehicle plus SST required from the for the second vehicle, because then both vehicle require that much gap or length of the road in between, so that both of them can really come to a stop condition without any head on collision. So, the total distance is calculated here as 207.12 meter. Now, stopping side distance what is provided is normally adequate for normal condition or general operation. It may be inadequate under complex or instantaneous complex situations, or where drivers have to make complex or instantaneous decisions. Number 2, where information is difficult to perceive. Number 3, where again drivers have to make unexpected or unusual maneuvers. Under these conditions, the available stopping side distance will not be adequate. So, at complex or critical locations, there could be error in either information reception, decision making, or control actions. For example, interchange and intersection locations. One can, there is a possibility that unexpected or unusual maneuvers are required. Vehicles may come suddenly. Similarly, wherever there are changes in cross section, such as toll plaza and lane drops and areas of concentrated demand, particularly areas of concentrated demand in urban environment, there could be visual noise from competing sources of information, from advertisement, from other lights, traffic lights. So, competing sources of information, it may be difficult. So, in those conditions, decision side distance is provided, which will give side distance value higher than the stopping side distance. So, idea is at all complex or critical locations provide decision side distance, in short DSD, or shift critical locations to places where decision side distance are available. If none of these options are acceptable, means they are not practically possible because of the site condition and other constraints, then suitable traffic control devices should be installed to warn drivers about possible condition. So, decision side distance should be adequate to detect an unexpected or otherwise difficult to perceive information source or hazard that may be visually cluttered, to recognize the hazard and its potential threat, to initiate and complete the maneuver safely and efficiently. Considering all this, AASHTO suggests DSD values for difference avoidance maneuver for A to E. A is stop on rural road, B is stop on urban road, C is stop speed, path, direction change on rural road. Avoidance maneuver D is for speed, path, direction change on suburban road. Avoidance maneuver E, speed, path, direction change on urban road. For avoidance maneuver A and B, pre-maneuver time is increased. Whatever we considered as perception reaction time, that is the pre-maneuver time, that t value is increased, and the braking distance is added to the pre-maneuver component, because ultimately it is a stopping maneuver. So, equation is just like SST 0.278 V t plus 0.039 V square by A, but here the t is pre-maneuver time, not the reaction time of 2.5 seconds what we considered in case of SST. In case of DST, this t value is higher. For avoidance maneuver C, D and E, it is not the stop of vehicle. So, the stopping component, the braking distance component will not be applicable. So, pre-maneuver time remains as it was for avoidance maneuver A and V. Higher value is used, higher value than the reaction time, and the braking distance component is replaced with a maneuver distance based on maneuver times that decrease with increasing speed. So, essentially in this case DST is 0.278 V into T, but do remember that this T is total pre-maneuver plus maneuver time as discussed. Now, I have a few questions for you. Number 1, explain the terms lag distance and braking distance. Number 2, explain the difference between stopping side distance and decision side distance. Number 3, what are the different avoidance maneuvers considered for recommending decision side distance? Try to answer to these questions and also try to solve a problem. The available side distance for a stretch of road with 6% downgrade is 100 meter. The design speed for the road is 80 km per hour. Is the available side distance adequate for emergency stopping of vehicles? If not, what will be your recommendations? You may follow AASHTO approach for solving this problem. Now, I will try to answer the questions which were raised during the last lesson. Define the following cross section elements and discuss their functions: carriageway, shoulder and median. Carriageway is the paved travel width, it carries the vehicular traffic, so all the loading is taken by the carriageway. Shoulder is that extra portion on each side of the carriageway, it basically provides support to carriageway and provides space for emergency stopping of vehicles without disturbance to the through traffic stream or the moving traffic stream. Median is basically the longitudinal space separating dual carriageway. It separates directional traffic stream, so it enhances the safety and it works as a traffic control device. Then explain the terms building line and control line. You know, road is acquired up to the right of way or the land width. Beyond that, these building line and control lines, these things are considered considering the future need for expansion. So, it is basically an attempt to control construction or developmental activities in a way which will be or which will be beneficial or which will be advantageous for the acquisition of additional land in the future. Define camber, it is a slope, cross slope provided to the road surface in the transverse direction. So, it is a slope provided to the road surface, the carriageway in the transverse direction for the drainage of water. Amount of camber depends on the type of road surface, pervious or impervious. More impervious surface, lesser camber is required, and also it depends on the amount of rainfall. Heavy rainfall, more camber or more cross slope will be required. Less rainfall, lesser camber or cross slope will be required. What are the disadvantages associated with excessive camber? Transverse tilt of vehicle because of the camber, and this is will cause discomfort to passengers. It will also cause discomfort during overtaking, because vehicle has to go to the other lane most of the cases, particularly for 2-lane road with 2-way traffic. Formation of cross ruts where there is heavy rain, and also the tendency of vehicle to travel along the central line, which is called the central seeking tendency of vehicle, which is not good or acceptable from safety point of view. Discuss the function of curves and guardrails. Curves basically facilitates and controls drainage, strengthens and protects pavement edge, delineates pavement edge, present a more finished appearance and encourages orderly roadside development. And guardrail basically prevents vehicle from running off. So, wherever at the approach of bridge or high embankment or outside of outer edge of horizontal curve, wherever vehicles are prone to run off from the carriageway, we provide guardrail for safety or to enhance the safety.